That's it. I'm not taking.
Okay. So it's really a pleasure to be here. So, when I have been asked to give this talk, of course, the first thing is, what should I be talking about? And it's really complicated. I mean, there are so many fantastic topics that Ronit has been working for many years. And so at the end, I decided to choose the topic to be approximating the weight. And these three dots are especially important because I don't really want to specify what do we mean by the weight in general. Okay, so good. When I first met Ronit and heard about Ronit, the first thing that I heard was her fantastic works on property testing. And many, many years ago, people have been thinking, okay, so we have this framework of property testing, which is really great. We have been seeing some successful results, but what can we do next with that? And then some people, including Ronit, but also me, start thinking, okay, can we actually transform property testing thinking or results into sublinear algorithms? So, in property testing, we would like to do something optimally in a constant time, but can we actually get also some sublinear time or maybe constant time algorithms for natural combinatorial optimization problems? So, okay, doesn't really work well. Oh, maybe it's done. Oh, very good. Why? Okay. Yeah, so now it's on. So in 2005, I had really a privilege of co-organizing with Ronit and Christian Zolle and Mudhu Krishnan a workshop in Dutchtool, which had a title Sublinear Algorithms. So as you see, we actually brought fantastic collection of people. Can you see Ronit there? So this was still the time when Ronit, she was very shy. So she didn't really stand in the first row. So I had to kind of point where she's around. She's hiding behind everyone.
Can I just for a second? Ronit is standing next to our good friend and colleague Artur, who unfortunately passed away.
Yes.
So I just want to remember him for 1 second.
So we had fantastic collection of people, including Avner, including, okay, Sampath, who is Sampath here? Oh, okay, he's lost. So at that time, kind of the idea was, so we wanted to put together people from property testing and streaming algorithms, where the idea was that, property testing want to do something in constant time. In streaming, want to do something with very little memory. Can we actually transform this into something in between, so sublinear algorithms, without specifying whether this is space or running time? So the key three areas that we're interested in were property testing, sublinear time algorithms, approximation algorithms, and data streaming algorithms. When I was checking actually the abstract booklet, there was some like 50% of property testing papers, 50% of streaming, and the rest, which was some like 2 or 3 papers in sublinear algorithms. Why I'm saying that? Because at that time, the field of sublinear algorithms was just starting. So this was 2005. And so last week, there was a workshop on some approximations, I don't know, simplification, some algorithms, usually very fast algorithms. And I remember there was a presentation about, approximation, sublinear time approximation algorithms for some matching problems. There was a very long list of publications, but it started in 2007 or 8. So in 2005, really nothing has been known. I mean, very little has been known. So when I was thinking about what should I be talking about, I said, okay, in my opinion, Ronit made some fantastic contribution in many things, but including in this specific paper. So around 2000, Ronit was at that time working in NEC. So together with late Luca Trevisan and Bernard Chazelle, she took a look on the fundamental classic MST problem from slightly different angle. So what they were doing? So essentially they observed that Kruskal-like or MST type of algorithms often can just be reduced to some questions about connectivity. And this is something that maybe actually you can teach now in some CS courses. So for example, think in that way. Suppose that you are given a graph and all weights are either 1 or 2. If you know how many connected components are in the graph induced by weight 1, then you can tell what is the cost of MST. If you have, so then actually you know that exactly this number minus 1 edges will be connecting between, will have weight 2, will be connecting these connect components of weight 1. So this gives you very nice formula for the cost of MST, and actually you can easily extend it to arbitrary case when the weights are all integers from 1 to W. Okay, so what can we do with that? So we have this formula, and for example, very simple observation, if you are given such a graph, all weights are integers between 1 and W, you can find easily MST in linear, in time W times M. That sounds trivial, but when W is constant, I actually remember it's sometimes a good question for students, find a linear time MST algorithm when weights are even 1 and 2. And for many students, it's too difficult. Of course, we have Prim's algorithm, which is also able to do that, so it's not the only thing. However, the main thing is that with some smart thinking, one can try to actually do more with that. So, so at that time, there was a question, what is if we don't really want to find MST, but we only want to compute the cost of MST? Then essentially, the only thing you have to do is we have to compute this C sub k. So number of connected components in some graphs. And nowadays, this may sound trivial, but at that time, actually, the fact that one is thinking about computing the weight instead of finding MST was something very fresh. The bad thing is that if you want to compute this CK, you still need linear time. So that's somehow not very exciting thing. Even if you want to get constant approximation. You can have, for example, I don't know, few isolated vertices and the rest is, I don't know, complete graph. You won't find these isolated vertices quickly. So kind of you don't really have a good way of doing that in some linear time. But then actually, and in my opinion, this is actually an approach which was coming from property testing, I think, was that let's just consider graphs of bounded degree. So suppose that we are given a graph of bounded degree D, and think D is a constant. Then actually easy to see that if you want to check if a connected component is small or not, you can do it relatively quickly. If you want to check if the connected component has at most S vertices, you can trivially do it in S times D time. You're running essentially BFS. If you hit S vertices, you know it is there. And you will spend at most S D time. So this is some idea which has been very similar to ideas known for property testing. One can combine this idea with the fact that, okay, this is actually quite important thing, that here we have this in the weight of MST, we are allowed to have some additive error when the number of connected components is small. So essentially what they did, they observed that, when the number of connected components is large, we can easily sample them. Why? Because if the number of connected components is large, you know that you will have many small connected components, and you can just randomly sample them. Okay? However, when the number of connected components is small, still we can do some sampling, which will be actually amortized by this additive error here. And then one can argue actually by checking the variance that we still can actually analyze it very quickly. And I will not give you details, most likely. Many of you have seen this algorithm in the past or even were teaching it. So at the end, they were able to show that, okay, some actually clever random sampling arguments can be shown that we can approximate the weight of MST to within 1 plus epsilon factor with the number of queries, which is the total weight times the degree, the maximum degree, divided by epsilon square queries. And actually, this bound is tight. If you want to, one can actually slightly extend it. So we can have, if G has average degree D, we can obtain the same result essentially. And even if all the weights are in the range from 1 to W, then we can obtain the same result losing factor epsilon here. So what does it mean in particular? It means that for sparse graphs with small weights, this is a constant time algorithm. And nowadays we see many fantastic sublinear time algorithms. At that time, it was a rarity. So essentially, we're saying constant degree, constant number of weights, constant time algorithm, just telling me what is the weight of the MST. And okay, on its own, it's a very nice result. But actually, what I want to tell you also something is that I like that result. Some people like that result a lot. So people have been thinking, how can we extend it? So one of the first questions was, okay, what is the weights are much larger, the degrees are much larger. And for example, I have been studying the question of metric graphs. What are metric graphs? So you're given a set of points in metric space and you want to compute MST. Now, there is a big difference that, in this graph, the average degree is high, it's n-1. The weights, we don't really have any bound for the weights. So can you do anything? So in that case, this algorithm is slow. However, the ideas in that algorithm can be used to obtain something useful. So first of all, it's important to notice that in this graph, actually, we trivially need linear time to do anything. However, for metric graphs, these are graphs of size n squared. So sublinear time means little of n squared. So I had a very nice paper with Christian Zolle where we're extending the ideas from Ronit's paper and actually show that we can come up with 1 plus epsilon approximation of MST in time which is n polylog n. Yes. I don't use buckets. I know Dana does, but I will leave this to Talia, who will be. But the main idea is that by this formula, all what we have to do is essentially count the number of, or approximate the number of connected components in some graph. Threshold graph with maximum weight or cost, whatever. So this was very nice result. Then actually, so nice application because it was mentioned a few days ago. One can actually also come up with 2 plus epsilon approximation of TSP using this because MST is implying TSP cost, etc. Okay. Then there was another very nice result, which again was using the same approach. So for a long time, people didn't really know how to do fully dynamic streaming MST. And then there was a paper by Fraling, Hinding, and Zolle who gave a 1 plus epsilon approximation algorithm for approximating the weight, the cost of MST in polylogarithmic space. So this is Euclidean MST. A few years ago, actually, also had some further extension. We're studying the same, we're studying also in the fully dynamic streaming setting, the Steiner tree problem, the Steiner forest problem. And again, we got something like, this alpha 2 plus epsilon approximation. Alpha 2 is this famous Euclidean Steiner ratio, which is now something like 2 over root of 3. So again, we're able to use the same approach. The details are always actually quite complicated, but kind of relying on the same setting. Then I do remember actually that also something similar. So this is something different, but something similar. So we are actually having, at that time, 2005, some algorithm for approximating the weight of facility location. Oh, sorry. The main point was that we're able to come up with some formula, very similar to the formula for MST that was presented in Ronit's paper. We were able to obtain n polylog n constant approximate, so algorithm which runs in n poly log n time and gives a cost approximation for the cost of facility location. And here is actually another problem that I have been studying. So we're interested in the estimating the cost of KNN graphs, nearest neighbors graphs. What is the graph? So you are given a set of points in metric space, and for each point, you want to connect it to the K nearest neighbors. So this is a directed graph, the R degree is K. You're always connecting to the K nearest neighbors. This actual problem is has quite a lot of applications in some fields, and it's easy to see that one needs n squared time. So what we have shown is we obtain some bounds, and the goal is not really to think about the bounds, apart from the fact that they are tides, but really what we're doing is we were reducing everything to a simple task of approximating the degree of some vertices in some threshold graphs. So to some extent, this idea of coming up with some nice estimator, which reduces the very complicated problem to something which is much simpler, happened to be very useful there as well. Okay, so what I want to tell you that somehow, this type of ideas, starting largely from that paper, led to many papers, and I'm sure actually I miss many other papers which have been using this approach. And you should actually also think that this was the year 2000. So this was maybe 5 years after we got linear time MST randomized algorithm. This was, I think, maybe 2 years after there was n plus m alpha of n MST deterministic algorithm. So this was very early years where people didn't really think about approximating the weights or even constant time. So really, in early 2000, nothing or very little has been known in that field. And let me actually add that something has been known for metric or for geometric graphs. I want to mention, because Piotr is lying on the floor somewhere, he had some fantastic paper, which again, I think it's great. So you are given a set of points on a metric space. You want to find the shortest edge. No way to find one. You want to find the longest edge, and you can come up with two approximations easily. So people have been using some tools, and then there were some Ronit students, for example, Krzysztof and some others. They came up with many algorithms using that. But this was really just the beginning of the field. Nowadays, if you're going to any Stock, Fox, Soda, or whatever conference, high quality conference, then you will see sublinear time algorithms in top places. And as you have seen here, for those of you who have been here for more than one day, this was really the whole program at Simon. So that's something that hopefully the community appreciates. And you see, actually, now Ronit is moving forward. She's not staying shy somewhere at the end. So now she's in the front row. So thank you.
Thank you very much. We have time for one quick question, perhaps. That, Natalia.